Welcome to my speech on scaling ETH infinitely without UX and liquidity fragmentation. So first, as any good programmer, I actually really hate the word infinite. It's marketing. Nothing really scales infinitely. But what we can try to do is scale ETH linearly according to the instances of rollups or execution sharding without UX and liquidity fragmentation. So first, a little bit about me. I'm a consultant and researcher specializing in ZK, L2s, privacy, and DAOs. Most of what I work on right now is decentralizing provers and sequencers, as well as how to maintain atomic interoperability in fractal ZK L3s. So today we'll be talking about how does blockchain currently scale, how do we get it to scale infinitely, and then what do blockchains look like in the future, as well as when is that going to happen. So why this talk? I'm a bit of a grumpy programmer, so I always looked at blockchain like, this shit doesn't scale. And the reality is we have very few users right now. If we ever want to have even like 100 million active users monthly, it's not going to work. Blockchains will burn and you'll be paying thousands of dollars. So how do we actually fix these issues? And it wasn't until the last couple of years that we actually started having like really good options and methods to actually make blockchain scale in a sort of similar fashion to Web 2. So how do blockchains currently scale? And this is comparing Web 2 compared to Web 3, right, or blockchain. So how does Web 2 scale? So let's say Apple launches a new phone and you want to pre-order it. Maybe the first 1,000 users go to one server and they pre-order the phone and everyone's happy, right? But now if there's like 2,000 people trying to access the same server, it just kind of burns down, it runs out of resources, crashes, and then no one can order anything, right? So what Apple kind of does is they kind of go through like osmosis. They copy the state of the server onto another server, and then the next 1,000 people get it from server number 2. And they don't actually need to know what server they get it from. They're just pre-ordering the phone, right? Everyone's happy now. So Web 2 scales linear according to the amount of resources that you allocate to it. So if you have server with X resources, you get 1x scale. And you add another one of those, you get 2x. And it goes on and on. You have 1,000 servers, you get 1,000x scale. So how do blockchains scale compared to this? And the whole kind of point in blockchain is we don't really want to trust anyone. So we essentially go through this game of every single server on the network re-executes every single transaction to see the current state and to come to consensus on Daniel does not have 1 million ETH, right? And just to give an idea of how this is bad for scalability is, let's say that you have a network with 3,000 nodes and a block takes 5 seconds to execute. Essentially, you're wasting around the world about 4 hours of re-executing the same transactions over and over again. And this is honestly just wasteful and not how Web 2 works. So blockchains kind of scale linear to the time that it takes essentially to execute a block is linear to the amount of transactions. So if you have one transaction, maybe it's that first dot there, and then you have 2 transactions, that's how much longer it takes to execute that block. And that's simplified a bit because every transaction is different. A Uniswap transaction is more expensive than just send transfer. But the problem is we want, because it's a decentralized network, we want a normal computer like a MacBook to be able to run the network. So we essentially put an artificial limit on this is how many transactions we allow in a single block. And in Ethereum, it's what is it, 30 million gaps? So it's about 15 to 30 transactions per second, depending on what kind of transactions those are. So essentially in blockchain, if you have one server, you get that much scalability. But now if you add 2 servers, you still only have 1x scalability. If you add 3,000 servers, it doesn't help with scalability at all. It stays static, right? It helps with decentralization and it helps with censorship resistance, but it doesn't scale the network at all, adding more resources to it. So we came up with this concept of Ethereum 2.0, right? And the idea is, okay, let's split up Ethereum into 64 shards, and then we'll split up the validator committee into 64 chunks, and then 1/64th of each validators, or total validators, validate each separate shard. But there's issues with this. Like, each of those 64 shards has the security of 1/64 of the whole network. And then the other problem was interoperability. Like, how do these shards talk to each other? Like, do we lose atomic composability, like Uniswap being able to call a price feed? And we didn't really have a good plan for how to actually maintain interoperability. And so we scrapped Ethereum 2.0, and that made Vitalik very sad. So we came up with this newer concept of scaling ETH infinitely, and that's called the roll-up-centric Ethereum, right? And the idea is, okay, what if we do execution sharding vertically? So you still have a shard, a roll-up, but instead of it running directly on L1, it's a separate blockchain that does computation off-chain, and then it submits both the data as well as the proof onto L1 to prove that everything ran correctly. And again, this is execution sharding, it's just a better version. And hopefully, since you're here, you know a little bit about how L2s work. Again, so I won't go much into details on this, but again, you have a bunch of transactions on a separate blockchain. The data for that gets posted to L1 as well as a proof showing that essentially those were executed correctly. So when someone tries to withdraw money, Ethereum knows that it's like the correct transactions. And so in a roll-up-centric Ethereum, essentially we get back to kind of Web 2-like scaling. These are made-up numbers, by the way, just for sake of thought. Like, let's say Starknet scales Ethereum by 10x, and then OP is another 20x, then you get 20x scaling, and then you add some more of those, you get 40x scaling. Right? And the benefit of this roll-up-centric Ethereum is now each of those shards actually inherits the full security of Ethereum. It's not fractionalizing the security of the network. But then there's lots of problems with this design, right? So we'll just go through these one by one, and essentially, like, let's go through the first one. If you all of a sudden move all of the Ethereum users onto, I don't know, Scroll or one of these protocols, at some point, Scroll is going to become more expensive of Ethereum, right? It's going to have higher transaction fees than Ethereum, and then what's the point of that, right? So how do we fix this? So the crackpot team at Starkware had this idea of, let's just make more layers. L3s, L2s, L3s, L15s, and now everyone gets a layer. You get a layer, you get a layer, cool. And actually, it sounds silly, but it actually helps scale. It's sharding. You just create more and more shards, essentially. And this design is called recursive ZK, or fractal hyperbridges, or superchain. We like marketing terms. So the idea is that if you bridge from, let's say, L2 to L14, every one of those bridge steps is actually just as secure as using the ETH L2. Right? There's actually no additional security assumptions because each of the bridges use exactly the same circuit for bridging. So you can safely bridge from L2 to L3 to L4 without worrying about it. And actually, it's not even really bridging in this sort of fractal design. It's more of accounting. You just kind of mark where the funds are now. Right? And this kind of shows it. So let's say you're going from that L5 to that other L5, right? Instead of like Cosmos needing to jump through every single one of those points to get to that bridge, to that new spot, essentially in the recursive model, all of the funds are sitting in the same exact bridge contract. So any ZK sync L3, L4 doesn't actually move the money anywhere. It's sitting on ETH L1 in the same bridge contract. So you can just kind of mark it over. Like, it's not on this L5 anymore, it's over here, and you don't have to worry about bridging. And also, Optimism and Polygon are doing the same version, but instead of going vertically, they're going horizontally. So essentially, you deploy a bunch of L2s onto the same common bridge. And again, the funds are in the same place, so you can just kind of mark them over. And so now, with this design, we've fixed fees, right? Now, each of those shards has less users, so it doesn't become as expensive as one chain having every user using it at once, right? But now the problem is interoperability, right? Both from a UX standpoint of view as well as like it might be expensive to move funds from Arbitrum to ZK Sync safely. And it's not composable anymore. It's not a synchronous transaction, it's asynchronous. So you can have sort of interoperability of contracts within them that happens atomically. So here's an example of how current L2 interoperability works. So let's say you have some funds on StarkNet and you want to move it to ZK Sync. You can just bridge it over with like multi-chain, right? Now, please don't. Let's not create cross-chain bridges. That's a horrible design. Like there's lots of security risks with cross-chain bridges. So how do we do this trustlessly? Right? So what we can actually do is you can batch transactions from StarkNet L2 to L1, and then that sends it to the StarkNet bridge, or sorry, the ZK Sync bridge, and the funds appear back on ZK Sync. And this way you actually have a trustless bridge design. You don't have to do this individually. We can make bridges that essentially batch 10 users into the same bridging transaction, and then essentially the ETH gas cost that you pay is 1/10 of an actual bridge transaction, right? And this works, you get the bridge funds. But it's also asynchronous, it's expensive, even if it's 1/10 of a ETH transaction cost. And it takes a while, especially with optimistic protocols. It might take 7 days to do this. So it's better, we can kind of solve this in the designs, the fractal or hyperbridge designs, where you essentially, again, you have all the funds on the same contract on L1, and then any of the L3s or L2s building on the same bridge contract essentially don't have to go that way through L1, right? And this is, so let's say the money is here in the bridge contract, which is actually a contract on L1. So when you want to move it from Coinbase L2 to optimistic L2, again, you just kind of mark that it's over there. And you don't have to have this, well, you'd still have to have the 7-day delay, but you don't have to pay the same amount of gas fees, right? And this works for bridging, but it's still asynchronous, and now there's MEV. Someone might see 7 days before you move that transaction over that, oh shit, this guy's gonna trade on Uniswap, and they can front run your transaction and steal money from you. So the way that we could, like one example, the original example of how we could actually fix this asynchronous component is, okay, let's have Coinbase L2 and Optimism L2 use the same sequencer, essentially. And this way, the sequencer essentially orders transactions from both of the chains. And now you have atomicity the same way that you have on ETH L1. And this way you actually have composability and no MEV. But now it's a beefy node. If you have 100 different L3s all using the same server, like we're not going to get that much scalability from it. It might be cheaper, but we still kind of want to keep L2s decentralized. It's not the same kind of security assumptions that you have on normal blockchains, because even if it's not decentralized, they can't steal your money. But we want some sort of censorship resistance and decentralization for the sequencer role. And you can call this one beefy sequencer to rule them all. Not a great design, even if the ring had a good thought behind it. And so how do we do this? How do we keep like decentralization and keep the nodes relatively small? So what we can do is we can have one sequencer that is shared between both of those chains. That sequencer doesn't execute the transactions. It literally just orders them. So it puts the Coinbase transaction, then the Optimism transaction, and it doesn't actually execute them, which is the expensive part. Ordering is super cheap, and just adding values to, if you've used Excel, it's like adding another value to it. And so we can keep that server very small. And then every other L3 or L2 can essentially execute its own transactions later. And this way, each of their sequencers are relatively small. They only have to worry about their own state and their own transactions. And again, they agree when they're going to insert the transaction. And then you can bridge funds over. And this actually keeps atomic composability and its small nodes. Right? But there's still the issue of like, now Coinbase chain doesn't know the state of optimism, so maybe you submit the transaction to swap ETH from Coinbase to Optimism chain and then back. But by the time it gets executed, it's like the price has moved, and all of a sudden your transaction fails, now your money's somewhere else, and it becomes a pain in the ass. Again, because it gets executed later, anyone that runs nodes for both of those networks can front run your Uniswap transaction, and they have lots of time to do that, so that's not ideal. So we can essentially add, if you've heard of PBS in Ethereum, this is a bit more in depth, just this topic alone, but we can essentially have Suave style proposer builder separation, where essentially the Suave builders run nodes for both of the chains, and then they see that, okay, you have a swap coming through and they're running the state, so they know the state of each chain, and they can actually promise you that this Uniswap transaction will not fail. So when it executes a little bit later, it's guaranteed to happen. Right, and now you have composability and no-fail transactions. But MEV is still an issue. Again, now the Suave builders see your transactions coming in and they can be like, oh, we can make some money off of this guy. And even without telling the network, they can again front run your transaction. So now we can add threshold. Yeah, this is not a simple thing, the interoperability of like doing this, but the hope is that, again, the user wouldn't have to know anything about this. So we can have a new transaction type called a threshold encryption transaction, and essentially you send that transaction with the transaction header public, but now you encrypt the body, so they don't see that you're swapping on Uniswap. And at this point, they include it in the block like they promised. And then block n+1, they essentially, so the next block, they decrypt it and then they say, oh shit, I could have made some money off of this swap, but now it's too late. It's already included in the chain, right? And now you have composability, small nodes, and no MEV in this sort of like roll-up centric Ethereum world. And a cooler sort of thing that you could do with this, just to explain why this is exciting, is like, let's say you have Uniswap as a L3 or Uniswap on Ethereum, and you want to swap some tokens through it. Cool, it works, you get your money. But the problem is, if 100 people are swapping on Uniswap, all of a sudden your gas fees are going to get really, really expensive, right? So what you can do with this sort of sharded fractal design is you can dynamically keep creating new instances of Uniswap, the same way that you do in Web 2 with the Apple server, keeps creating new instances as the demand needs it. And again, your coins are not in those shards, they're on the lower level. So now you can dynamically swap against any of those instances. And you don't actually even need to know I'm connecting to this L3 or this L3 or this L3. It's just like through an RPC level, we just show a swap happened, and now you have, you know, some USDC instead of ETH. And now you actually get like a Uniswap contract that can scale dynamically, essentially infinitely, as long as you keep adding new instances of it. And in the future, like when that demand goes down, you can actually delete those instances because it doesn't matter what the state of that specific shard is, it matters where the money is. So now we actually fixed like interoperability. So all of a sudden you don't need to think of which L3 or L15 you're on. It just kind of works. You can trigger a contract and it happens, that interaction. But now you have all these roll-ups, all these L15s, L12s that essentially need to submit their data onto Ethereum. And that's a lot of data, and Ethereum can't really handle that kind of data. So what can we do about that? So this guy named Dankrad thought about that, and he's like, wait, we do that already. Every data center uses something called erasure coding. We could apply the same to blockchain, right? So here's kind of how dank sharding works, and I'm sure you guys have heard about this. And this is more of a mental model than an accurate picture of exactly what percentages of erasure encoded data is, and it doesn't go into elliptic curves. The idea is currently in Ethereum, every single node on the network needs to hold all of the data, right? And that's why it becomes a problem, because if you have 15 rollups putting the data on chain, your node requirements are going to go up a lot, right? So with dank sharding instead, we can essentially hold just one chunk of the data, right? And then the problem with if you only hold one chunk of the data is like, what if this guy disappears? Now that blue block is gone, right? So what we can do is we can hold one chunk of data plus another 25 to 50% of erasure coded data, of the data from other people's blocks, right? So now if the same guy disappears, the three that are left can essentially use their erasure coded data to reconstruct the missing data, right? But now the problem is you're only holding a small part of the data. You also have the erasure coded data, but how do you know that all the data in Ethereum's history is available, right? And that would be a very big problem if any of it disappears, because it would break the blockchain. It could never forward anymore. So essentially, you can send some queries to the network, like random queries. So let's say there's 100,000 blob data points. You just pick a random number between 1 and 200,000, right? And that's the data that you're asking for. And from the first sample, essentially if someone returns the data, there's a 50% chance, just statistically, that all of the data in Ethereum's history is available. Then you do this again, random number, you guy, give me some data. Now there's a 25% chance that anyone could have lied, right? And by the time you do this 30 times, there's essentially a 1 in a billion chance that that data might not be available. And you can keep doing this as long as you want, to the point that it's like, even if there is a chance that someone could have hidden data or deleted data, it's like statistically next to impossible, right? And cool, now you know all the data is available, right? But what happens if someone actually does delete the data, right? Like, what if part of that data is gone, now you don't have the full version, so shit, Ethereum's broken, right? So what you need with erasure coded data and full dank sharding is you need at least 75% of all of the data to be available to reconstruct the missing 25%. But the benefit of this is, like, that sounds a bit scary because maybe it does disappear, but the reality is, like, any person in the world can hold a full copy. And even if most people don't have that data, they can't lie about the data. They can't just like create fake transactions into it. Essentially, we can check against the data against the hashes. So as long as Coinbase or you at home or literally anyone else holds all the data, we can essentially continue Ethereum, and there's like no problem. Every node's storage requirements are smaller, and we'll never end up in the situation where the data is not available. And a cool part of this dank sharding thing is, like, sometimes we have these shit coins. I mean, sorry if there's anyone that likes frogs. That happen on mainnet, and all of a sudden gas fees spike up a crazy amount. And shit, that's bad for L2s, right? Maybe L2s can't continue. But with dank sharding, you actually have this sort of two-dimensional gas market. The gas market that rollups use is completely different than the gas market that normal contract execution does. So even if there's another shitty NFT that spikes up the cost of Ethereum, rollups can continue functioning without any negative externality. So all of a sudden Arbitrum doesn't stop because there's an NFT mint. And so cool, we fix all these issues. ETH is infinitely scalable, right? Right? Not really. We still need to fix other shit on L1. And unlike some Bitcoin and Solana people have been claiming, we haven't forgotten about L1. It's just like, this is execution sharding is the thing we were working on since ETH 2.0. So that's kind of prescient. So how do we fix issues in L1? What can we do? So the first thing that we can do is we can do parallel execution and localized fee markets. And essentially, we already have the ability, when we make a transaction, we can declare access lists. So we can declare we're about to touch this part of Uniswap, what part of state we're touching, and this wallet, right? And if we declare those, if we're forced to declare those, essentially we can do two very cool things. The first is, all of a sudden, any transaction of me sending Miko 1 ETH, you can parallelize all of those transactions. So you can execute them at the same time without worrying about it. But that only has limited applications. Like maybe if Visa wants to run transactions on ETH, parallel execution would be great if we're going to have 100,000 transactions a day or second. But for the shared state, you can't really do anything about that. But we can do another cool thing with that called localized fee markets. So again, if there's a random frog coin or NFT that spikes with localized fee markets, essentially that contract's interactions would get much more expensive, but it wouldn't affect the price of Uniswap at all. So people could continue swapping on Uniswap without being hurt. And again, we can do this on L1. If we don't do it on L1 because it'll break some contracts, which it will, we can at least do this on L2s. The other thing that we want in Ethereum L1 is statelessness. And essentially we can move the storage structure to something called vertical trees. And again, right now the kind of issue for nodes is every single node needs to hold the entire state of Ethereum. And that's about 1 terabyte currently. It'll keep growing, but you can't really load 1 terabyte into RAM, into memory, so you have to store it on a hard drive. But a normal hard drive is not fast enough, so you need a SSD hard drive. And a 2 terabyte SSD hard drive is kind of expensive, right? And if we want this protocol to be decentralized, like we can't have that kind of barriers to entry of like 200 might be cheap for us, but if someone in a developing country wants to run a node, that's prohibitively expensive. So with statelessness, essentially we create full witnesses of each block, and essentially this way each node does not need the entire history of Ethereum to run the next transactions. They can essentially just download the current state. And with that, you could essentially have like mobile phones. Like this would take about 1 gigabyte per device, so your iPhone would have enough space to be a full node on Ethereum. ZK for L1, this is not a if, this is a when, this will happen. We will make Ethereum ZK, like the actual execution layer and the consensus layer. And the benefit of this is like going back to how blockchains currently scale, again, we have to kind of limit the amount of transactions that can happen because we don't want it to be a Solana supercomputer that runs the network, right? So with ZK, essentially, whoever proves the transaction still has to do a lot of work, but every other node on the network doesn't have to run that transaction at all. They can just verify the proof, and if there's a proof for those transactions, you know the other guy executed it correctly. Right? And actually, we don't even need one computer to do this. It's really easy to parallelize proving. Let's say you have a block of 100 transactions. You can have 100 different computers proving one transaction completely separate of each other, not worrying about it. In this way, the verifiers are small computers as well as any execution nodes are small computers. And that's essentially the scalability we can get in L1 from ZK. And with this, essentially, you could have an iPhone essentially being a full node. You could have your MetaMask be a full node on your computer, and you wouldn't have to connect to any RPC, and we get much more decentralization, as well as then we can increase actually that block limit of how many transactions are allowed. In Enshrined rollups, I'm running low on time, but essentially with Enshrined rollups, essentially the consensus of the L1 has the rules of the rollup instead of being a separate blockchain. They would share the same contract for verifying proofs. This is under active research. It's going to take us 10, 15 years to come to consensus on how we should do this, but we will have that in the future as well. And so how does this affect blockchains in the future? The hope is that by using in production and researching all these topics in L2s, whether it's ZK or shared sequencing for interop between shards, we can actually use this to apply it back to Ethereum. And we can come up with the execution sharding 2.0 that's actually interoperable and inherits the full security of Ethereum, right? And so when token? Just kidding. When scalable? Soon. Give us like 10, 20 years. It's gonna take a while. This shit's not easy. But if we do get here, we can actually get blockchain adopted by like the world. Like there's no way Visa or normal companies are gonna use this if it doesn't scale. And if we do figure this out, you'll see Vitalik clap. It's really fun. Like, it's worth it. Just all these years of work and engineering is enough just to get Vitalik happy. And the point of this presentation is, unlike some blockchains, Bitcoin, some blockchains, no code is perfect, no protocol is perfect. We need to keep working on this and figuring out some of these scalability issues if we actually want adaptation in the real world. And we need to do it in a way that your grandma or your mom can use it and they don't keep having to switch chains or worry about the security in moving funds between different chains. And we talked today a lot about ZK. It was a small field of us cryptographers, math nerds that liked ZK for a long time, but don't ask a cryptographer how to explain ZK. They'll go into polynomial commitments and Friday-based recursion. This is a mostly mathless version of understanding how ZK works. Bridging is a long conversation, whether it's cross-chain bridging or in L2s. I do have a speech on that just to break down each security compromise. And again, L2s have their own security issues. We had a panel at ETH Gathering where we talk with some teams about what their issues are and how to fix those. And that's it. You can follow me on Twitter at ZK-Lumi. I don't do a lot of shit posting in the small community of ZK L2s. We have Togrul for that, so. But I do put up some research sometimes or any new speeches, and you can follow me there. Thank you.